people get like very terrified of calculus, I feel like, for no real good reason, because calculus isn't really that complicated. It's essentially looking at a kind of pattern and just seeing where that pattern leads you, basically. So I'm going to be starting this with sequences, or actually, I guess, series. So I'm going to look at a very simple series. I'm going to be looking at what happens when I just keep adding 1/2 to 1/4, right? Which is 1 over 2 squared, plus 1 over 8, plus 1 over 16, plus 1 over 32, dot, 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 all the way to 1 over 2 to the n, right? So basically this is just, I'm going to rewrite this as 1/2 plus 1 over 2 squared plus dot, 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 all the way to 1 over 2 to the n, right? So how can we, is there like a pattern that this follows? Is there some type of number that this approaches? Well, I'll begin by rewriting 1/2 as 1 minus 1/2, because notice that if I just have this first part, I can write it as just 1 minus that first part. And that might seem like an obvious thing, but what I can do now is I can split up that 1/2 into 2 quarters, right? So I can say 1/4 and then minus another quarter. Or 1 minus 1 over 2 squared minus 1 over 2 squared. But notice that's exactly what we're adding in the next term. So if I do 1/2 plus 1 over 2 squared, or 1/2 plus a quarter, that'll be the same as 1 minus a quarter, right? So, and this pattern kind of just keeps going like this. So every time I add a new member in this, I guess, kind of like sequence, like, 1 over 2 to the n, the result will always be, so if I do 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus dot 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 plus 1 over 2 to the n, the result will, I will always be able to write the result as 1 minus 1 over 2 to the n. That's essentially the idea. And so now I can kind of calculate what this will be for any n. But the idea now is that if I kind of do this infinitely, right? If I let n approach infinity, what's going to happen to this result? Where will this result lead us, or where will this sum lead us? And if you really think about it, I mean, if n approaches infinity here, then you get 2 to the, like, a really large number, which means you have a really large number in the denominator, which means that the result will be very small. So the larger n is, the smaller this result will be, or really, the smaller this result will be, the smaller the thing that we're subtracting by will be, right? And so as n approaches infinity, this kind of like sum, I guess, sum will approach 1, because this part will approach 0. But notice that we can never kind of reach 1, no matter how many times we do this kind of thing, no matter how many times I add a new member to the sum, I will never reach 1, but I can always get closer to 1. And that is kind of the central idea of calculus. It's kind of doing a very discrete process and looking at where it leads you in that kind of limit as something like approaches something. And I use the new word here, limit. So what I'm actually doing here is I'm taking the limit as n approaches infinity. So I'm going to introduce a kind of new notation, by the way. You might not have heard of it, but it's summation notation. So if I have the sum like if I have the sum from when n equals 1 to 2, for example, and I have like 2 in here. So what that means is I need to let n equal 1. I need to kind of go through every single number that n can be. So n has to go from like 1 all the way to 2, and that's kind of where it ends because that's the top part. So basically what this means is I write whatever is in here for n equals 1. So this is where like n equals 1. And then I add to that another 2. That's whatever is in the sum at kind of n equals 2. I realize that might not make a lot of sense, so I'll kind of do another example, I guess. Let me make n go between like larger numbers. So I let n go from 1 to say 5, and instead of 2 in here, I guess I think it would make it more clear if I wrote n in here. So what I'm doing now is I'm trying to sum all n from when n equals 1 to n equals 5. So what this means is I'm just saying 1 plus 2 plus 3 plus 4 plus 5, and that's where I end that whole like sum, right? So I go from n equals 1 all the way to n equals 5, and that's where I stop, right? So in this kind of like thing. And what I can do, the other thing I can do, or another thing I can do, is I can change this n to say n squared. And now instead of just writing n in here, I can write, so I'll have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And then that's where it ends again, right? But now I have these like squares, which will make the number larger. So I can use this piece of notation to rewrite this sum in this kind of manner. I can say the sum from when n equals 1 to n of 1 over 2 to the n, right? Because that's kind of what this means. I have n equals 1, so that's 2 to the 1, just 1/2. And then I'll have n equals 2. That's just going to be 1/4, right? Because 1 over 2 squared, and so on. So this is how I can kind of write this entire sum. And so, like what we've shown here through this little investigation is that we can write this whole thing, right? As n approaches infinity, the whole sum approaches 1. The way we mathematically express that is the limit as n approaches infinity of the sum from when n equals actually wait, I think I should replace this with an I realize, because it's kind of confusing. So when from when I equals 1 to n, I should say, because it's a little confusing. But anyway, so so I'll write as n approaches infinity from when I equals 1 to n of 1 over 2 to the n equals 1, right? Because 1 is that kind of limit. So what this result means, what this says, is that I can pick some kind of number, some really small number, let's call it epsilon, that's greater than 0, and I can just have, I can take this limit, right? I can take this limit and subtract from it the sum for when I equals 1 to n of 1 over 2 to the n. So this whole thing that we have in this limit. And then if I subtract these two, let me make this a little larger. If I subtract these two, I can make this result as small as I want. So I can have some kind of, I can think of some kind of epsilon that's greater than 0, that's as close to 0 as I want it to be, and I can always make this whole thing like the absolute value of this difference here. I can always make this less than epsilon, because that's what it means for the limit to be 1, because I can just pick enough terms, and if I pick enough terms, I can eventually make this whole thing in here as small as I want it to be, right? Because we've shown over here that we can rewrite this whole sum. We can rewrite the sum as 1 minus, so this whole sum equals 1 minus 1 over 2 to the n. So I have 1 minus 1 over 2 to the n. And so what I'll have is these ones will cancel, and I will basically end up with 1 over 2 to the n right in there. So, and this must be less than some number that I can think of, epsilon. So, and that's kind of the point, right? I can think of some kind of number, epsilon. I can make it like 0.0001, and I can always think of an n that's large enough that will make this whole fraction smaller than epsilon. I can think of infinitely many n's that will satisfy this kind of inequality. So if I have like epsilon equals say 0.1, I can just say n is, I can pick an n larger than, I'm going to make it greater than or equal to 4. So if I let n be greater than or equal to 4, then this thing, right, 1 over 2 to the n, will be less than or equal to 1/4. No, not 1/4, sorry, 1 over 16, which is less than 1/10, right? So this is 1/10. So that means I can pick any number greater than 4. I can pick any number greater than or equal to 4, and I can just plug that into here, 1 over 2 to the n, and I will end up with a result that is less than my epsilon. It will satisfy this kind of condition here. And if I'm not satisfied with that, I can just pick an epsilon that's even smaller than that. And the point is that I can make epsilon as small as I want. And that's what it means for this limit to be the thing that it is, right? That's what this limit is saying. It's telling it, that's what it means to kind of approach a value. It means that I can pick an epsilon as small as possible, and I can kind of pick a larger value for n. So as n approaches infinity, this thing is satisfied. So if I pick an n, there's kind of like a threshold thing going on, right? So if I pick an n that's larger than some n, I can always make this whole thing smaller than epsilon. That's basically kind of the point. All right, so next time I guess I'll cover like a more rigorous definition of this whole thing. This is kind of a very unrigorous introduction, but hopefully it kind of helps. Let me know if it does. But yeah, that's all I have for this one today. Bye.